So I just wanted to do a shout out here to the 11 different members of the Terra Hunting Consortium, with Didier Kalo being the principal investigator. This is really quite a big international effort here. So definitely huge thanks to everyone who's involved there. A nice visual here from Sam to show you where we're trying to get with this experiment. So this is sort of a quintessential plot that you've probably seen variations of throughout. So on the x-axis, you have orbital period in days. On the y-axis, you have mass in terms of Earth mass. And then the planet data is color-coded by stellar mass. And you can see where that sort of 50 centimeter per second line is dashed. And we are trying to push underneath that towards the green line, really trying to get towards that other Earth scenario. So pushing towards the lower amplitude, longer period planets. Oh wait, do we have an issue? Okay, so I have no idea where I am in terms of the time, so I'm just gonna continue and roll with it. I believe those of you in person got to see this slide, but those of you online did not. Basically, the idea is that we want to push towards longer period planets with smaller amplitudes, targeting those sort of temperate or rocky potential Earth 2.0 sort of jobs. Now I can't move forward the slide. Oh, there we go. Whew. Got it. So what is the Terra hunting experiment for those who are unfamiliar with it? Also, I will point out that I had no part in naming this. It's a nice name if you say it out loud, but the maybe could have worked on its acronym a little bit. Nonetheless, we're going at a 10-year program where the goal is to get 10 centimeter per second RV signals of planets that are around a GK dwarfs. We're going to have a really intensive observing strategy in this, and the idea is that to observe each of our stars every single night. So our sample will be like a standard star in other surveys. And we want to have at least a minimum on-sky time for each target of 6 months per year, but a longer season is better. Sam Thompson and some others are working from a simulation point of view to try to optimize the observing strategy. And sometimes there might be more than one observing baseline that could potentially be optimal. Our exposure time is going to be primarily driven to reach a certain signal to noise. And then after that, the next constraint is looking at what the pressure mode oscillations are doing for our K stars. Those are probably going to be averaged out to reach the signal to noise. For the G stars, we may have to expose a little bit longer to bend them out. If we have a really bright target, we might be able to have a very short exposure time and then look at modeling those out. The idea is to probe a new planet discovery space. This is a similar parameter space that some other instruments are interested in. So looking specifically around 600 to 400 day orbital periods and trying to probe down to 1 to 4 times the Earth mass. Really, the idea is to demonstrate that these planets could potentially exist and then to detect them. This is going to have some synergies with those future direct imaging missions that we heard about, potentially the Habitable Worlds Observatory or the LIFE mission, because they're going to be looking at bright nearby targets, which is the same overlap there. So we're hoping to be able to provide them with targets and to get masses for at least some of them. If you want more information on our Terra hunting goals, go ahead and check out the website for some more details. So a little bit more on what our typical star looks like and what sort of precision we expect. So for a G magnitude star brighter than 7.5 magnitudes, that's where we're looking for. Again, that G to K stars. This leaves us with potentially 50 stars to be surveying, but we want at least a minimum of 22. And again, like I said, that minimum observability of 6 months per year, but more if we can. We will also look at a particular stability check. If there are other planets in the system, then we will take that into mind when we're searching at a particular parameter space. If you want to know more about that survey design and strategy, Samantha Thompson is working on a paper that's in preparation, so keep your eyes peeled for that. A lot of this is being based off the work from Richard Hall, though, so do go ahead and check that out. Ultimately, we're aiming for about 1,500 observations per target star over 10 years. And one of the main drivers for this intensive strategy is because we want to be able to sample well those stellar signals, as well as sample well any of those multiplanetary systems that might potentially be in there. And so we also want to avoid issues with aliasing and so on. Along the way, we will also be taking spectropolarimetry measurements. The exact cadence of those observations is yet to be determined. Our goal, though, is to have really bright stars and to be better than photon noise limited in terms of our RV error budget. So as the name suggests, this is HARPS3. This is going to be more or less a clone of HARPS and HARPS North, but with an upgraded RV accuracy goal of 10 centimeters per second. So we're looking at a stable fiber-fed high-resolution instrument, higher than 100,000, with the full visible wavelength range from 380 to 690 nanometers. We'll have 2 fibers that are simultaneously with simultaneous calibration modes. The efficiency is listed here, but do note that some of our optical components still need to be measured. And so this is just kind of a guideline, and those efficiency values are somewhat under construction. The goal, though, is to have HARPS3 be fully roboticized. So there is a SPIE proceeding that talks about this a little bit, but we'll come back to it a bit later. So again, that calibration unit, there are 8 switchable light sources allowing illumination of fiber A or fiber B in any combination. And one of those will be a deployable full Stokes dual beam polarimeter. And then another one of those is going to be our solar telescope, or BARS, which will have spectropolarimetry, and that is being led by Annalise Mathieu. So do go ahead and chat with her online. I think she's in the EPRV RCN, so check her out on that Slack channel if need be. As Suva said, the sort of standard is to have octagonal fibers and double scrambling. That is where we're heading for as well. And we will be using the data reduction software that is based off the Espresso pipeline. Oh, I should also note that the calibration light is scrambled in the unit before being injected into the cassegrain. And so our laser frequency comb actually has some really exciting developments. So Suva, I've mentioned that it's hard to go bluer than about 500 nanometers. That is indeed the case, but our goal is to have the full wavelength coverage, to go from 380 to 690. And we're working with Harriet Watt to do that. And we've got some exciting preliminary results to show you. So we've got comb spacing between 18 to 30 gigahertz, absolute wavelength accuracy down to 1 to 2 centimeters per second, and an automated comb locking. We can't show you everything that Harriet Watt is working on here because they have a paper in preparation, but in the spirit of trying to show you where we're at and what we can. This is a plot showing you the output from the laser frequency comb, where I want to highlight that the x-axis is in frequency here. And in the vertical dashed lines, you can see 500 and 390 nanometers highlighted. And so you can see that we're getting some excellent throughput here. And this is a nice prototype in terms of thinking about what the Andes laser frequency components could be on the ELT. Again, the laser frequency comb is then utilized with a fabric Perot cavity in order to give us the laser frequency code modes and give us the mode spacing that we need. Here, it's locked on 34 gigahertz and showing you an example with a resolution of 40,000. So this is some exciting stuff in terms of trying to get a laser frequency comb that works in the blue. We're on track. And do go ahead and check out the Harriet Watt team here and follow them for the paper that's coming. So where is HARPS3? It is going to be installed on the 2.5 meter Isaac Newton telescope in La Palma in the Canary Islands. We plan to refurbish that telescope, and part of that is also to make it fully robotic. The contract is signed and going, and we've recently had a successful preliminary review there. And so the idea is, again, this photon noise, for an example, for a star of 7.5 G magnitude, we're hoping to get 25 centimeters per second and have that nightly access for 10 years. And really, the beautiful thing with this is the Terra hunting experiment will be on sky for about 50% of the time. And then the other 50% of the time will be open to the public. Running out of time here, just want to show you some pretty pictures of actual HARPS North pieces here. So we've got a custom optical table and the collimator mount. The collimator is in the final polishing stage. The vacuum vessel is mounted on the aligned rail system in Cambridge there. You can see the shell grading. This arrived in the lab early 2020 and had a first inspection, and then we immediately went into lockdown and were locked out of the lab. And then you can also see the HARPS3 CCD there with 4K by 4K pixels. So I will just go ahead and leave the summary slide up here to tell you about the Terra hunting experiment and take any questions. Thanks.
Thank you very much, Heather. Questions? Yes, please.
Great talk, Heather. I have a question about your Q observations. You mentioned that a fraction of it is available for the community. And it sounds like you have lots of nights. So are you out of the bright time only curse? So you will also use the dark time of the telescope?
Yeah, I think so. I don't think that there is a specific requirement for I think it's a mixture of both, but maybe someone in HARPS3 in the audience can correct me if I'm wrong there. Otherwise, we can ask Sam Thompson, who will be checking the Slack channel as well.
As far as I know, it's getting a percentage of the total hours of observations, and that will be in principle spread over all nights.
Yeah.
And unless there's some transits or something like that that are from the open time panels, they get mostly some time in all the nights.
One question there.
Yes, very simple. You've shown the LFC accuracy for about 2 centimeters per second or less. I was wondering and asking you if you have an idea of the stability of this accuracy in time. So you expect it to be stable for 1 year, 2 years, 5 years? I don't know.
So the honest answer is I'm not an instrument person, and so I don't know, but I believe that it is going to be stable over the year's time scale. Again, shout out if that is incorrect, but I believe so.
Okay, I have one quick question.
Yep.
You mentioned the improved stability of this HARP3 system. If you had to name the single upgrade, the single improvement that moved from the HARPS earlier meter per second level, now it's a bit better, to the 10 centimeter per second, what would it be?
That's probably a question for Francesco. I guess or maybe Xavier, I don't know, actually. Do one of you want to shout out and what your gut feeling is? I'm glad it's making you sweat a little at least.
Can I need my lawyer. No, I think that there is no specific item. I think the laser frequency comb is one of the key issues because on HARPS South or HARPS North, there is no laser frequency comb working on HARPS South. There is one, but it's not integrated in the standard operations. Here by concept, it must be working actually. And I think that's the first difference. And then the others is that we, for example, Xavier mentioned the problem we had on HARPS North with the cryostat. So this hopefully will, this kind of small technical aspects will have been solved such that the third version of HARPS will be perfect.
Yeah, and of course, we can also take advantage from the software side, all the advances that have been made over the years and stepping on the shoulders of Espresso in particular here. So that would be very useful.
Very last question there.
I should have talked for longer.
Hello, thank you for the nice talk. So is there any plan in motion to minimize the number of times you'll have to open the instrument during its lifetime to avoid having multiple offsets in the radial velocity time series over the 10-year time scale? Thank you.
Francesco's laughing again. So, I mean, I guess by the very natures, we're trying to minimize it as much as we can from the outset. Yeah.
Yes, I mean, of course, you want, I don't know in which talk it was mentioned, but basically you want to avoid a zero order effect. So you want to avoid opening, reopening, heating up the detectors, things like that. Now, conceptually, it should be possible if you want to do a long-term experiments, and I will come back later to that if we do discuss about calibration, to do whatever you want with the instrument, and then you should be able to recalibrate it. That would be the ideal word. But since you cannot guarantee that from the beginning, I think, yes, we should not open HARPS3 more than, than needed. Okay, avoid whatever is on. So there, I'm not sure there is a spec on that, but it's certainly a goal.
Thanks, Francesco.
Okay, thank you very much.